Astronomy and Astrophysics, Taiwan, and at the Inter-University Center for Astronomy and Astrophysics, Pune, India. He worked. I guess I'm fixed now. Sorry, I guess I'm fixed now. Sorry for the convenience. I guess I'll start again. So hello and welcome again to this talk. Today with us we have Dr. Manoj Purvankara. He is currently a faculty member at the Department of Astronomy and Astrophysics, DIFR, Mumbai. He is part of Infrared and Optical Astronomy Group at the department. Before joining Astronomy Group, he worked as a research associate at the University of Rochester, NY, USA, and was a postdoctoral fellow at the Academia Sincere Institute of Astronomy and Astrophysics, Taiwan, and at the Inter-University Center for Astronomy and Astrophysics, Pune, India. He worked for his PhD at India Institute of Astrophysics, Bangalore, and obtained his post degree in 2005. His primary research interests are the area of stars and planet formation. His expertise in star formation, optical astronomy, infrared astronomy, planet formation, photometry, star infrared, astrophysics, and observational astronomy. So this will be a very good talk, and before we start, we'll also have a few announcements to make. So after this talk, we'll have a quiz in which we'll ask questions based on this talk, and you can participate in it and and get an e-certificate, and this is our, I guess, 12th talk in this series. So yeah, I'll transition to you, sir. Yeah.
Thank you. Shall I start? Okay. Thank you. Thank you very much. And thank you, Jameer and other members of the Antariksh Astronomy Club for organizing this talk and for giving me this opportunity to give this talk. I'm really happy to be here to be able to share with you some of the a bit of history and a few exciting new results from the field of exoplanets. So I'll directly jump into my talk. The title of my talk is 25 Years of Exoplanets, What Have We Learned So Far? Now, clearly, before we ask what have we learned so far, we need to, you might ask me what are exoplanets, or why 25 years. So let me explain to you that first. Exoplanets are planets orbiting stars other than the sun. And the first such planet was discovered around the normal main sequence stars other than the sun in 1995. And for this discovery, a Nobel Prize in Physics was awarded to the discoverers, two Swiss astronomers, last year in 2019. So the 25 years, it has been 25 years since the first discovery. So that's the relevance of 25 years. And then this sets the context for this talk. So until about 1995, the only planetary system that we knew of was our own solar system, right? And I have in this figure above here that you can see above the title, I have tried to capture this historical fact. I have chosen to illustrate it in a plane defined by orbital distance in the horizontal axis. The orbital distance is given in the units of astronomical units. One astronomical unit is the distance between Sun and the Earth. And on the y-axis or the vertical axis, I have planet mass in the Earth mass units. I have also shown all the 8 solar system planets here, as you can see. The Earth is at 1 astronomical unit and it has 1 Earth mass, of course. So all the terrestrial planets are here: Mercury, Venus, Earth mass. Can you see my cursor? I'm assuming that you can. Yeah. So all the terrestrial planets are here, and the giant planets and the ice giants are here. So Jupiter is at 5 astronomical units, 5 times as far as the Earth from the Sun, right? And this was the situation in 1995, and these are the solar system planets. And the first exoplanet was discovered in 1995, and that was a sort of Jupiter mass planet, but very close to the central star or the host star. But 25 years later, the situation has dramatically changed. So this is what it looks like 25 years later. I let it blink between 1995 and 2020. You can see the difference, right, already. The color code here is for different detection techniques. Don't worry about it so much at the moment. So you can see that we now know of more than 4,000 exoplanets. And you can see from the orbital distance, so most of them, a good number of them, a significant fraction of them are within the orbit of Mercury, right? And there are a bunch of Jupiter-like gas giants at several tens of AU, or several tens of astronomical units, very far from the host star. So what I'm going to do in this talk is to explain to you how we got here from 1995, where we had our solar system planets and just 1 exoplanets, to 2020, where we have over 4,000 exoplanets known. And then from in the last 25 years, what have we learned about planetary systems? In 1995, before 1995, we had only 1 planetary system, and now we have over 4,000. So this certainly this has added to our understanding of how the basic architecture and properties of planets, and also the formation of planetary systems. So that's going to be the gist of the talk. So here is a rough plan. I'll start with a brief description of the discovery and the technical challenges involved in that discovery, and the impact that the discovery of the first exoplanet has made. And then I'll describe a few detection techniques. So how do we detect exoplanets? See, this is not trivial, you know, it's not by some magic that we have detected this many. This requires a combination of a lot of things, that technological advance, skillful deployment of these technologies to detect these very faint signals. So most of the exoplanet detection techniques are cutting edge or frontiers of research. I will then briefly describe the current, summarize the current census, and finally I will describe to you what we have learned so far from these over 4,000 exoplanetary systems that we know now. So first, the discovery. So the first detection of a planet outside of our solar system, around a sun-like star, was reported in 1995 by Swiss astronomers Michel and Didier Queloz, for which they were awarded the Nobel Prize in Physics in 2019. The Nobel citation says for the discovery of an exoplanet orbiting a solar-type star. The keyword here is solar-type star. See, the first exoplanet discovered was not this. It was not in 1995. It was in 1992, around a dead star, a pulsar. But it soon we realized that there aren't pulsars, or dead stars don't host many stars. So this was in 1995, what the discovery was, the detection of a first exoplanet around a normal sun-like star, which astronomers call the main sequence star. So they employed a technique called radial velocity technique. So let me show this movie to you to explain how this is. So So basically, the planet is moving around the star. The planet is too faint, and we cannot detect the planet. But when the planet is moving around the star, so in fact, what the star and the planet is moving around the center of mass of the system. So star is also moving. You can see star is also going around, right? So the star we can observe, star is bright, and star we can observe. And you can see the star is sort of, I'll play this again just to clarify the idea. Uh, so the star, during its motion, the star is coming towards you and moving away from you. Suppose if you are looking at the plane of the orbit, now star is moving away from us. Now this and now it's coming towards you. So we can do obtain spectra of the star, keep monitoring the spectra, and in spectra we have photospheric lines of corresponding to different elements in the star, and then if you monitor these lines, when the star moves away from you, you will see. I'll play this again. When the star moves away from you, you will see the lines to be red shifted. So I'm sure you have learned about the doppler shift, right? When the emitting source is moving away from you and coming towards you, the frequency changes. So the same thing happens to the spectral lines. When it's moving away from you, the lines get red shifted. It moves to the longer wavelengths than the rest wavelength. And then when the star is coming towards you, as it is doing now, it gets blue shifted. And that is what is shown here. So it's probably explained better here. So here the observer is at the bottom of the screen, and you can see the star coming towards. When the star is moving away from you, that's a maximum velocity. That's when the red shifted. When it's moving away from you, red shifted. Coming close to you, blue shifted. So essentially, you can see the lines here. The line. So you have several lines in the spectra of the star, and they all start moving back and forth. If you can detect this movement, these relative shifts of these lines, then you can estimate the speed with which the star is moving, and that you can connect to the mass of the planet orbiting. And this is exactly what Michel and Didier Queloz did in 1990, they reported it in 1995 in Nature, and they discovered a planet of mass, half a Jupiter mass, orbiting around a sun-like star called 51 Pegasi. And this is what is shown here is the radial velocity shifts, the way in which lines shift. So this is a red shift, and then this is the blue shift. So it is a periodic shift. So once you have such a radial velocity curve, the way in which the lines move back and forth, then you can directly measure the period of the orbit. So this is one period. So you can immediately measure the period of the planet. So orbital period. So how much time it takes to go around the star, and what is called radial velocity semi-amplitude, which is basically this amplitude. And that amplitude K is directly connected to the planetary mass. So you can measure period and K, the radial velocity semi-amplitude, from which you can measure the planetary mass. And this is exactly what they did. When they measured the period of 4 days and the mass of about a half Jupiter mass to the first exoplanet detected around the sun-like star. So this expression for radial velocity semi-amplitude can be written in different ways. Here, I have written it in terms of Jupiter mass, and here for Earth mass. So what I really want to highlight here is that Jupiter around Sun would produce a radial velocity semi-amplitude of 12 meters per second, and Earth around Sun would produce a radial velocity semi-amplitude, the velocity of 9 centimeters per second. So what I'm trying to describe to you now is the challenge, the technical challenge in measuring this. So this was not an easy measurement. In fact, the Nobel Prize awarded to this discovery is not because it has led to some new physics or some unknown discovery, but to the technical difficulty and involved in this discovery, and how people overcome that difficulty. And so that just to illustrate that, I've shown this: the Jupiter, to detect a Jupiter-like planet around a sun-like star, uh, uh, Jupiter with a period of 12 years, like that of Jupiter, the velocity shift that you have to measure is 12 meters per second. And let me tell you how difficult that is. So to measure a velocity shift of 12 meters per second, you need a radial velocity measuring precision of 2 to 3 meters per second. All right. Now, so you of course have to do this in a using spectra, so using a spectrograph or a spectrometer, and typically the resolving power of a spectrograph used for this purpose is about 50,000, the lambda by delta lambda. That is how the resolving power is measured. Or in other words, the delta lambda, the spectral resolution, is about zero 0.1 angstrom. And you typically want to sample your spectral resolution over at least 2 pixels of your detector, and which means your dispersion is about 0.05 angstrom per pixel. I hope you know the unit of angstrom. You heard of it. It's 10 to the minus 10 meters. So 0.05 angstrom per pixel corresponds to 2 to 3 kilometers per second per pixel in velocity units. But then the precision, radial velocity precision that we require is 2 to 3 meters per second. So 1,000 times more or 1,000 times lower. So what we need to the measurement that is required to measure or detect exoplanets, one must measure wavelength shift to a precision of 1,000th of a pixel for a Jupiter-like planet. For an Earth-like planet, the precision will be 10 to the minus 5. 1 in 100,000 or 1 in 1 lakh of a pixel. So typical detectors, the charge-coupled devices, have a pixel size, the picture element size of 15 micrometers. So what this involves, detecting exoplanets is measuring motions of stellar lines, moving back and forth, to a fraction of a nanometer. That's the kind of precision that you require, and that is why it was not discovered until 1995. It's such a difficult measurement to make. So the difficulty is the following. See, most general purpose astronomical spectrograph. So you need your spectrograph to be very stable, extremely stable, to be able to measure a fraction of a nanometer or even a nanometer shift in their lines, which is a thousandth of a picture element. But then the astronomical spectrographs that astronomers generally use are not that stable. Then the solution for this difficulty is to the precise instrumental calibration with an absorption. So I'll discuss in a minute what that is, or to separate your spectrograph from the telescope and keep it in a stable environment so that you can maintain the stability. So the two solutions to obtain this RV precision, one is absorption cell spectroscopy. What this means is that you place a cell of gas of iodine or hydrogen fluoride in the place of in the path of the starlight, where the starlight enters your spectrograph. So you also have this iodine or hydrogen fluoride line. So they also suffer the same instrumental shift as the starlight. So you can relatively calibrate all changes that happens because of the movement of the spectrograph. So this technique was pioneered in the early 80s, 90s by the Canadian group of Bruce Campbell and Gordon Walker, and the Berkeley group of Jeff Marcy and Butler. The other technique is to use a stabilized spectrograph, remove the spectrograph from the telescope and keep it in a stable thermalized, thermal and temperature and pressure controlled atmosphere, and then measure obtain the spectrum. And this was first demonstrated by Latham et al. In '89, and the Nobel Prize winning discovery was made using this technique, using a stabilized spectrograph, decoupling it from the telescope. So here I show a historical evolution of the radial velocity precision, the velocity precision in the units of meter per second on the vertical axis, and the year in which it is achieved on the horizontal axis. So you can see most of the velocity precision achieved fall in this line, except there is this outlier, the Canadian group, the pioneers who mastered the gas cell technique. So the interesting thing to note is that even in 1980, 82, they have achieved the same radial velocity precision as the discoverers who used LOD spectrograph in Switzerland. They had similar resolution. It's just that they were looking at wrong stars. See, if they had looked at any one of the 200 nearby stars, which we know have host planets now, if they looked at any one of them, they would have detected in 84 itself. So it's really a interesting story how the Canadian group missed out on this. So I'll skip this history example, and then so after this discovery, this is the first discovery of a planet outside of a solar system orbiting a star other than the sun. This had a profound impact on the field. So it sort of, until then, the exoplanet field was in the margins of astronomy, astrophysics, and this discovery really ignited the field and gradually moved it to the center of the astronomy itself. And so this, and in addition, this discovery generated so much interest that it made people start developing new detection techniques, and I will describe a few of them soon. And it also provided impetus for very highly productive space missions. NASA's Kepler mission was one such example. I will describe. I'll list a few in the next slide or so. And as I said, it propelled exoplanetology into becoming a principal area in astronomy. So the first discovery using this technique, radial velocity technique that I just described, that sort of prompted the development of several other different techniques, and the most interesting one was the transit method. So something like 75% of the exoplanets known, out of the 4,000 exoplanets known, is now discovered using what is called as a transit method. And then there are various other methods. I will probably talk about the first four, and will not have time to mention or describe the other three. Yeah, so this discovery sort of prompted or provided impetus for planning several space missions. And many of them are listed here. The prominent of them is the Kepler mission, which was launched in 2009, and now the mission is over. So this has tremendously advanced our understanding of exoplanetary systems. And of the 4,000 exoplanets, 4,000 or so exoplanets that we know now, close to 3,000 are discovered by Kepler, about 3,000 or so. So then there is another mission called the TESS mission, which was launched in 2018, and there are several future missions. So I'd like to point out that our space agency, Indian Space Agency, ISRO, is planning a exoplanet mission to be launched sometime in 2027, 28. It's still in the early phases, but this mission is more or less on. So now let us look at some of the detection techniques. I have already told you about these various techniques, and radial velocity I have already described. Now let's look at transit method. So transit method is basically looking the dip for say if the planet is moving around the star, and when it blocks the starlight, then you see there is a dip in the light curve. So you keep looking at the star, and then when the planet transit, there is a dip, right? So if you can measure the depth of this, so this depth is proportional to the area, the ratio of the area of the cross-sectional area of the planet to the cross-sectional area of the star. So it's basically the radius of the ratio of the radius of the planet to the ratio of the radius of the star squared. So that gives you the depth. And from the transit method, you can measure the radius of the planet. Here is an example of how the radius dependence of the transit method. So you have a large planet here and a small planet here. So the star is the same. So the large planet will have a larger transit depth, and the smaller planet will cause a smaller transit depth. But you could also have multiple planets, right? So then your light curve, when you keep monitoring the star, you would see something like this. The first planet is transiting now, so it's dipping, and now and it's back. And the second planet is now entering the stellar disk. Now it's dipping, and while the second planet is still there, the third planet is also entering. And so you can get all kinds of complicated light curves, and there are ways to extract information out of it. But the point to remember is that the transit method gives you the radius of the planet and also the inclination angle. So you remember in radial velocity, we could measure the mass of the planet. Uncertain only to the extent of how the orbital plane is tilted with respect to you. If it is perfectly perpendicular to your line of sight, you will get the true mass. If it is slanted or slightly tilted with respect to your line of sight, you'll get a minimum mass of the planet. But at any rate, the radial velocity gives you the planet mass. The transit method gives you the radius of the planet and the inclination. So if you observe a planet using both radial velocity method and the transit method, you can measure the mass and radius of the planet. Once you have mass and radius of the planet, you can start talking about the bulk densities, and that itself is already interesting. So this is truly remarkable that planets around the stars far away from us, and we can actually talk about the densities of these planets. And in fact, about I think close to 600 or so planets we have both mass and radius measurements, and one can estimate bulk densities and then start talking about the composition of the planet, whether they are rocky planets like our Earth, or they are giant planets like Jupiter or Saturn. So moving on, so as I said, the transit depth is proportional, or gives you, it's a ratio of the planet radius to the stellar radius squared, and that gives you the radius of the planet. There are these two techniques, but let me not spend too much time on it and move directly to give you some numbers here. And the reason why I don't want to spend too much time on the other two is, see, as you can see here, radial velocity technique and transit method account for 96% of the exoplanets known to date. So these are the most prominent techniques. So other methods are slowly catching up, and the situation might change in next few years or so. But at the moment, most of the planets that we know, over 4,000 exoplanets or so, are detected or discovered by these two methods. So here is the current census of all the known exoplanets. What is shown here is the cumulative number on the vertical axis and the discovery year in the horizontal axis. The red color corresponds to radial velocity and the green corresponds to transits. Let's just focus on them. So you can see initially, I mean, right from the discovery in 1995, it is all radial velocity, red, right? I mean, until about 2013 or so. So 2009, Kepler satellite was launched in 2009, and it employed the transit method to detect exoplanets. And by 2013, the Kepler data started becoming available. And then you see, after 2013, the green bars started dominating. Basically, the transit method starts dominating. And you can see now in 2020, almost 75% of the known planets are discovered using transit method. And transit method and radial velocity technique account for more than 96% of the known planets. So we now have, this is the current number of this is of 20 as of 24 June, but this might have slightly changed. But yeah, close to 4,200, over 4,000 confirmed planets, and more than 4,500 candidates, which needs to be waiting to be confirmed, and that is happening and progressing as we speak. So these numbers are going to go up at a rapid rate. Out of this 4,000 odd planets, 700 of them are in multi-planetary systems, meaning there are more than one planet in 700 systems. So this is the current census, and so let us just, so they come in all kinds of flavors. The diversity that we see in these planetary systems are huge. So here is one such planetary system. See, until about 2 years or so, I mean, until 2 years ago, our solar system had the unique distinction of hosting 8 planets, but not anymore. This particular system called Kepler 90, this has 8 planets, just like our solar system, but very different in architecture, though. And there is another system, and I'm just trying to give you the diversity, the sheer diversity of exoplanetary systems that we are unraveling and discovering. So this system called TRAPPIST-1, this is around a star called TRAPPIST-1, which is a cool star, a star much cooler than Sun, and much smaller than Sun. And there are 7 planets around this star. But this entire planetary system is within the orbit of Mercury. It's a very extremely compact system. It's very different from our solar system. We also have systems which are very extended. For example, this system, this was one of the first systems discovered by direct imaging. So this is around a star called HR 8799. See, what I'm showing you here, so the central star is, the light from the central star is blocked, and then you can see the 4 planets at different distances. What you actually see is orbital motion. So this video is made by images of these planets from 2009 to 2016, and they are juxtaposed on each other, and you can actually see the planets moving, the planets changing their position. So this is harmonic motion in nature in action. But these planets are, so unlike the earlier system, TRAPPIST-1, which was a compact system, these are very extended. These are 4 gas giants at 15 to 75 astronomical units. Our solar system's extent is about 30 AU, right? Or 30 astronomical. Neptune is at about 30 astronomical units. And this is beyond, extension beyond. So this particular planet, the farthest one is at 75 AU, and the closest one is at 15 AU. So you have such systems as well. Yeah, so we have this amazing diversity and the sheer number of planetary systems, and now it's possible to carry out a meaningful statistical studies of these systems. I mean, about planet properties and the planetary system architecture. So the observed properties of the planets are radius, mass, and the orbital period, and we can look for various statistics. I know how. So, what kind of planets are more common, and is our do these exoplanetary systems look like our solar system, or are they different? How do their architecture different from our solar system, etc. So it's possible to answer these questions now, and our group have been working on this for the last few years, and hereafter I'll give you some of the results that have come out of our studies and studies elsewhere. So this is so now we are moving into the part of what we have learned so far. And So these are the three important points that I would like to highlight that we have learned so far in the last, let's say, 25 years. I'm already giving you the results, and in the rest of the talk, I'm going to explain to you or describe to you how we have arrived at this conclusion. So I'm first giving you the results and the important properties that we have learned about these exoplanetary systems. The first one is that planetary systems are ubiquitous in our galaxy or even in the universe. In fact, there are more planets in our galaxy than stars. What this means is that there are more than one planet on average around a star. And I will tell you in a moment how we arrived at this conclusion. The second important result, interesting result that we have learned about exoplanetary system is that solar system is not an archetypal planetary system. It's not a representative planetary system at all. Most of the exoplanetary systems that we know of so far do not look like our solar system. And the third one, perhaps the most important one, is that the planet properties, the measured properties of planet, namely the mass, radius, the orbital period of the planets, are closely connected to the host star properties. It's almost as if the planet knows what star it is born around. So it's very interesting, and it has very important and profound implications for our understanding of how these planetary systems form. So let's look at how we arrived at these results. So the first one, planetary systems are ubiquitous in the universe. That there are more planets in our galaxy than stars. So to do this, one computes what's known as occurrence rate of exoplanets. So occurrence rate is simply the mean number or average number of planets per star, having properties in a specified range, having so number of Earth-like planets around a sun-like star, for example. And you just estimate this occurrence rate by number of planets detected divided by number of stars surveyed. Suppose if you had a survey, you have a perfect survey, you surveyed all the stars in our galaxy. You looked at all the stars in our galaxy for exoplanets. And you discovered exoplanets, planets in around X number of them. Then it's a straightforward thing. You just the number of planets detected divided by number of stars surveyed. But unfortunately, our surveys are not complete. There are other issues like selection biases and all of the selection effects and observational biases. So one needs to correct for all this. So if one understands a survey very well and its limitations, the selection biases and selection effects and observational biases, one can indeed correct for this. And this was particularly done for the Kepler survey. So Kepler survey employed the transit method to detect exoplanets. So one has to correct for the geometric probability of transit. So you imagine you don't detect, even if you are capable of detecting, you don't detect all transits. So suppose you have a planet around a star and it's face on. Like the planet is like this and it's moving like this. The planet is going around the star like this. So it is never going to, and you are observing, you are observing or I am observing, I'm the observer. So I'm never going to detect a transit because the orbit is face on. It's not perpendicular to you. It's like this. So the planet is moving around like this. It will never block the starlight. So you will never detect it. So so one can calculate the geometric probability out of a random number of distribution. If the orbital plane is randomly distributed in all angles, ranging from 0 to 90 degrees, what is the probability, geometric probability of detecting a transit? So one can calculate that. Then even if a planet is transiting, whether you can really detect it, is your instrument sensitive enough to detect it? So you need to work out that probability. Then and other details like NOS level. I don't want to go into the details. We can, if anyone is interested, we can discuss this. There are ways of accounting for this, factoring this in, and getting the true occurrence rate. That is the fraction of number of planets detected, around stars. The average number of planets detected around stars. Let me show you some of these results now. Uh, from these studies, we have been able to show that, so this is one such result. What I've shown here on the vertical axis is the occurrence rate per 100 stars, number of planets per 100 stars. And this is shown as a function of planet radius expressed in the Earth radius unit. So you have Earth-like planets here, super Earths, planets which have a radius which are 2 to 4 times the Earth radius, and ice giants, which ice giants are in our for solar system analogs. They are Neptune and Uranus. Neptune has a radius of 4 Earth radius, so Neptune and Uranus will fall in this bin. And gas giants, Jupiters and Saturns, Jupiter-like and Saturn-like. And these are the occurrence rate. Just to show you this, and so these are the terrestrial planets or Earth-like planets, what we call in our solar system, and these are the ice giants, Uranus and Neptune, and gas giants, Jupiter and Saturn. And when you calculate the occurrence rate for them among the exoplanets that we have discovered, it turns out that the smaller rocky planets are more abundant than the gas giants. So for 100 stars, there are about 58 Earth-like planets, about 60 super Earth kind of planets, but only 7 ice giants, Neptune, Uranus kind of planets, and about 7 gas giants. So the giant planets like Jupiter, Saturn, Uranus, Neptune, they are fewer compared to smaller Earth and super Earth kind of planets. This is one of the interesting results that have come out of the exoplanet studies. But what about the total occurrence rate? So if you collapse all the radius thing and find the total number of planets around stars, so that works out to be about 1.3 planets per star on average. This doesn't mean that you have 0.3 planets on a star. This is just an average number, the statistics. So what this means is that on average, a star hosts more than one planet. And that is why once talk about more planets than stars. So in our galaxy, it looks like there are more planets than stars. There are, on average, more than one planet per star. And this has been the major contribution of Kepler satellite. So it has showed that the planetary systems in our galaxy are ubiquitous. Most stars in our galaxy host planets. Not only that, most stars host more than one planets around them. So that was the first result. The second one is about our solar system. So it looks as if our solar system is not a representative planetary system at all. And why do we say this? Here I show the distribution of the planet radius, the frequency. Planets, the planet radius is given in Earth radius, and I have shown the radius of Earth here in the red line here, radius of Neptune 4 Earth radius, and radius of Jupiter. So you look at this distribution, it peaks around between that of Earth, it peaks between Earth and Neptune. So what it tells us is that the most common planet in our galaxy or has a radius between that of Earth and Neptune. We now call it a super Earth or a mini Neptune. So these planets seem to be the most common ones. Interestingly, our solar system does not have one. Our solar system does not have a planet in between, with radius in between that of Earth and Neptune. But most common exoplanet seems to be this variety, which we now call as super Earths or mini Neptunes. Secondly, here is a distribution of the orbital periods of the exoplanets known, and I show the orbital periods. Orbital periods is given in days, so 365 days is that of Earth, and Mercury is 88 days. See where it peaks for exoplanets or exoplanetary systems. It peaks around 10 days or so, 8 to 10 days. Mercury, which is the innermost planet in our solar system, has an orbital period of 88 days. So most of the exoplanets or planets orbiting other stars are very close to the host stars. They have much shorter orbital periods. So they are much more compact than our solar system. So our solar system looks very unique. And finally, here is a scatter plot of planet radius as a function of orbital period. Again, I've shown the solar system planets here in red: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. You see, most of the planets are well within the orbit of Mercury, and there are very other interesting things also in this diagram. But I just want to make a point here that solar system does not look like an archetypal or representative planetary system in terms of planet properties or the system architecture. The final result that I want to share with you, highlight, is this. So this has really come as a surprise. I mean, nobody was expecting this. So it looks as if the observed planet properties, such as the mass of the planet, the radius of the planet, and the orbital period or the orbital distance of the planetary system or the planet, is very closely connected or very closely related to the host star properties. So let me explain to you what I mean by this. So first, let us look at the relation of planet properties, namely mass, radius, and orbital period, as a function of the host star spectral type or the effective temperature. So I hope you understand the effective temperature or the spectral type of the star. Star has a temperature. When in the night, when you look up at the sky, you might find some of the stars look red and some blue. That is because they're at different temperatures. So it looks as if the planet properties dependent on this temperatures of the star. Here is another way of understanding it. Typically, you divide them into spectral types. So basically means the stars, the coolest stars have temperatures around 2000 to 3500 Kelvin. You understand the unit of Kelvin, right? In temperature. Yeah, so they would look very red, and the K-type stars between 3500 to 5000 Kelvin, and G-type. Sun is a G-type star. It has temperatures between 5000 and 6000 Kelvin, and when you go further up, it becomes hotter and bluish. But most of the exoplanets that we have discovered, of the 4000 or so exoplanets that I was talking about, was mostly found around these sources, these spectral types: stars, host stars, stars with temperatures in this range. So we'll only be talking about them. So let us see what we find. So what we find is the following. Here I have shown the occurrence rate again, number of planets per 100 stars, as a function of spectral type of the temperature of the star. So M type is the coolest, K type is the next slightly warmer, and G type is sun-like, still warmer, and F type is really hot. So as you can see, most of the so M type stars, the coolest stars appear to have more planets. And then when you go to warmer and warmer host stars, the number of planets decreases. Right? So for coolest stars, the M type or the coolest stars with temperatures of 2000 to 3500 Kelvin, there are on average 2 planets per star. But when you come to sort of F type stars hotter than sun, there less than 1 planet per star. So the number of planets per star is also a function of the temperature of the star. This temperature of the spectral type of the star is also a proxy for the mass of the star. The cooler stars are of lower mass, and hotter stars are of higher mass. So G types are sun-like. These are about 1 solar mass, similar to the sun. These are less than 1 solar mass stars. I mean, and F types are stars which are more massive than sun. So stars more massive than sun appear to have fewer planets. So that is what it looks like at the moment. So next, uh, so cooler stars indeed host more planets, but how about the radius distribution of those planets? So that is what is shown here. Uh, uh, so I have shown again the occurrence rate, or the number of planets per 100 stars on the vertical axis. Now, as a function of planet radius, and the spectral type of the star is now shown in different color bars. The red is for M type, the cooler star. Green is for K type, the slightly warmer than the M types. And G type, the sun-like stars. And the F type stars, more massive or more hotter than sun. So you see the cooler stars, the M type stars, the red bars. The M type stars host mostly Earth-like or rocky planets. So you bear in mind that the 4 Earth radius is the Neptune things, right? These are the ice giants and these are the gas giants. So the red bars you see only around smaller planets. So these are the giant planets, ice giants and gas giants. So these planets are not found around M giants, cooler stars. So cooler stars like do not host many giant planets, but they host many more Earth-like or rocky planets. So that's another result that I've come out of it in terms of, when you look at planet properties as a function of temperatures of the stars or the mass of the star. Lower mass star or the cooler stars have more planets around them, but most of them are rocky planets, smaller planets. Whereas hotter stars or more massive stars, sun-like or more massive stars, have fewer planets around them, but they preferentially host Jupiter-like gas giant planets. Finally, I want to look at this host star properties called stellar metallicity. I'm not sure if you know what metallicity is. So let me try to explain in what this is. See, the most abundant element in the universe is, of course, hydrogen, followed by helium. So hydrogen and helium account for 98% of the universe. All the other heavy elements is only 2%. So astronomers, by metallicity, astronomers mean this 2% of heavier elements. So when I say, so you can measure the metallicity of star. What it tells you is that the degree of metallicity, what the fraction of heavy elements in these stars. Stars are mostly hydrogen and helium, 98%, but the metallicity measures what the fraction of heavy elements in them. The higher the metallicity, more heavy elements, presence of more heavy elements in the host star. Okay. But what is interesting is that the observed planet properties show very strong correlation with the metallicity of the host star, the star it's orbiting around. So this, nobody was expecting this, and this is now a well-established result. So what it means is that if you, so this is a statistical result. What it means is that if you look at the metallicity of the stars without planets, stars with small planets, rocky planets, and stars with giant planets, what you find is that stars with giant planets, stars which host Jupiter-like or Saturn-like planets, have higher metallicity. Whereas stars which host smaller planets, Earth-like planets, have lower metallicity, and on average, and stars which host no planets have even lower metallicity. Or in other words, so this is a statistical statement, but what we find is that giant planets are preferentially found around stars which have higher metallicity, higher content, heavy element content. This sort of explains this. I show this as, again, occurrence rate on the vertical axis. Occurrence rate meaning number of stars, number of planets per star. And the horizontal axis has the planet radius. So here are the Earth-like planets. Here are the mini Neptunes or super Earths. Here are the Neptunes or the ice giants, and here are Jupiters. And the bars, the color bars show the metallicity of the stars hosting these planets. The green one is solar metallicity. Metallicity is similar to that of sun. And the red one is subsolar metallicity. Metallicity is high, heavy metal, heavier element content, which is less than that of the sun. And the blue bars are for host stars, which have metallicity or the heavy element content higher than that of the sun. You clearly see when for the blue bars, when higher, so supersolar metallicity host stars host more Jupiter-like or gas giants. But one of the results that have come out in the last 2-3 years is that although when the planet mass increases, the metallicity of the host star increases, but after about 4 Jupiter mass or so, this metallicity trend does not hold. So what this means is that planets which are Jupiter-like are preferentially found around metal-rich stars or stars with higher heavy element content. But planets which are much more massive than Jupiter, there are this category of planets called super Jupiters. They don't seem to follow any such trend. They can form around stars with any metallicity. So we were one of the first few people to demonstrate this, and this has very interesting consequence or implications for our understanding of how planetary systems form. This is a different illustration of the same effect. Yeah, it's 7 o'clock. So let me summarize what I have just sort of described to you, the results, basically what we have learned so far in the last 25 years. So I have chosen to highlight 3 results here. It doesn't mean that this is all that we know. We know much more interesting, many more interesting things. You cannot explain all of them in 1 hour, but I have chosen to highlight these 3, and I'll summarize them now. And in the discussion after the talk, we can maybe I can talk a little bit about other interesting properties that we have discovered about exoplanets. So to summarize, the first of the result that I wanted to highlight today was planetary systems are quite common. The occurrence rate, the average occurrence rate appears to be 1.3 planet per star. So this basically means that there's more than one planet around every star in our galaxy. But there are finer details to this. So the smaller planets are more ubiquitous than gas giants. There are many more smaller planets than giant planets. And there are more planets around cooler stars than sun-like stars. So our solar system is around sun, but most of the planets are hosted by stars which are much less massive and cooler than sun. The second important result that I discussed today is about the solar system. A solar system appears to be somewhat unique. It's not a representative planetary system from what we know so far. So why do I say this? So it lacks the most common planet that seems to be around, namely a super Earth or a mini Neptune. And it also do not have close-in planets. Most of the planets that we have discovered around other stars are very close to their host stars. They are very compact systems. But our solar system, they're much more compact than our solar system. So some of this is probably selection effect because we have not explored the entire parameter space. So we are missing out on, perhaps we are missing out on solar system-like planets. But nevertheless, what we are finding is a population of planetary systems which are very different from our solar system. See, the existence of these systems, these compact systems, cannot be denied anymore. They are there. So as far as we know, from what we know so far, around the 4,000 odd exoplanetary systems that we have discovered, they don't look anything like our solar system. Yeah, is there a question? Sorry. Uh, yeah. So the final point that I want to make is this uh, this correlation, this the mysterious correlation between the observed planet properties and the host star properties. Uh, so I've described how planet properties such as the planet radius or mass and period are strongly uh, it looks as if they depend on the host star properties, such as the effective temperature of the star, or spectral type, or the metallicity of the star. Uh, so larger and more massive planets are preferentially found around metal-rich stars, that is, which has higher, heavier element content. Uh, Cooler stars seem to avoid giant planets. Giant planets, or another the other way around, the giant planets are not found around cooler stars, but they host many more smaller planets than sun-like stars. Uh, so one interesting question. So this perhaps the third result is perhaps the most interesting insofar as the questions that it raises. So one interesting question that that this particular thing, this tight correlation between planet properties and their host star properties raises the so do planetary systems preserve their memory of their birth? So why would you see there is no reason why planet properties should depend on the host star properties, uh, but the fact that they do uh, perhaps implies that the planetary systems preserve their memory from their birth. Uh, it has important implications for planet formation theories. So we can maybe I'll stop here and I can take questions. See, some of I have described to you some of the observed properties, and uh, perhaps in the question and answer session I can I can explain, clarify why, or try to discuss what do these correlations mean, what do these various relations and results mean. I'll stop here and take questions now, I think.
Okay, cool. So we have few questions here. So I'll start with Mrunmi. So she asks, why are the radial velocities decreasing as years are increasing?
Say that again.
Why are the radial velocities decreasing as the years are increasing? So we had a graph in the start.
Why are the radial velocity decreasing
Decreasing.
as the
Years are increasing.
uh, so this perhaps refers to the cumulative histogram that I showed.
Yeah.
Perhaps it is. Oh, it's just that until 2013, radial velocity technique was the most prominent technique in town. And Kepler satellite was launched in 2019, and that employed the transit method. So it just looked at the piece of sky, 10 degree by 10 degree piece of sky, and just stared at that piece of sky for 4 years. And the first data set was released in 2013. And then the transit method started discovering many more exoplanets than radial velocity. As you can see, the radial velocity also, the number of planets discovered by radial velocity method also increases. But then the rise in the transit method was so rapid that it just overwhelmed the numbers discovered by radial velocity.
Got it. So another question is by Aditya Deshmukh. He asks, can you please tell us about NNX2 and K2 missions?
K2, yeah. What is the other one? First one?
NNX2. NNX2.
I don't know. I don't know what an NX2 is. So K2, see, K2 was a Kepler mission. See, Kepler, after 4 years of its mission, it's one of the gyros failed, and then the since it couldn't steadily look at the star, the photometric accuracy kind of drops, and then they that was sort of re the a different program. So the aims of the program was slightly changed, and it started looking at different patches of the sky, and that mission is called K2 mission. I don't know about the other one.
Okay. One interesting question by Pushkar. He asks, could the average orbital periods of exoplanets be lower because it is easier and quicker to detect exoplanets with lower orbital periods?
Yeah, that's true. Yeah, that certainly is true. And yeah, so all this, yeah, I think that is the caveat I probably mentioned in between. But so all these results that I just described, uh, I think strictly speaking, this applies only to planetary systems with orbital period less than 1 year, or orbital distance less than 1 AU. Although we have some correction factors and all that. And the reason is that most of these results have come out of the Kepler study. After 4,000 exoplanets known, close to 3,000, I think 2,800 or so are from Kepler. And Kepler mission was only for 4 years, and it just stared at the patch of the sky. And Kepler's one of the Kepler requirement was it has to detect a transit 3 times, at least 3 times to be confirmed. So it cannot confirm any planet with orbital period greater than 1 year, because the mission itself was 4 years. So Kepler is sort of complete only up to one orbital period of 1 year. Yeah, so Pushkar is right. Yeah, so so this is what I was also alluding to earlier. So we are not our understanding of extended planetary systems beyond 1 AU is not complete. We do know several such systems, but it's not complete.
There's a question by Nishant Pawar. He asks, can you shed some light on the citizen science projects and machine learning role in the study of exoplanets? Also, challenges ahead in research?
Yeah, I mean, I am not an expert on this, but yeah, so I can only say, yeah, it's probably useful, but yeah, yes, I think I'm not the right person to comment on this, so probably I'll just just not do that. Yeah.
Okay. Uh, okay, there are a few questions about metallicity. So the question is, does metallicity has to do anything with the age of the stars?
Yeah. So age in the sense, yeah, in the astronomical sense. Uh, See, there is a metallicity age relation in the sense that see, our galaxy is more than 13 billion years old, and some of the stars in our galaxy are as old. Some of the cool stars like M-type stars are 13 billion years old, and compared to those stars, the stars which are 10 to 13 billion years old, and the stars that are being born now are much more metal rich. The heavy element content is much higher than the old stars, and this is because see, when the generations of stars, see, stars also are born, they go through a middle age and eventually die when they run out of hydrogen. But some of these stars, like stars greater than 8 solar mass or so, they die spectacularly in a supernova explosion. Then they uh, disperse all the nucleus the heavy elements that they have synthesized in their core into the interstellar medium, from which the next generation of stars form. So when each generation of star form, their heavy element content increases gradually. So there is a relation of metallicity with age, but that happens over a much longer time scale. In fact, we recently, my student and I have found something very interesting. Since this question is asked, let me just show you. Yeah. So forget this axis. So just look at this age on the vertical axis and the planet mass. So we do find that giant planets or the Jupiter-like planet. Look at the planet mass. There is an Earth mass unit. 100 Earth mass is Saturn. and Jupiter is 300 Earth mass somewhere here. So you see the gas giants. Gas giants are generally younger in the sense 5 giga-years or so. So this is connected to that metallicity question. Whereas the rocky planets, they are found around older stars also. 8 to 9 giga-years are also. So, but giant planets like Jupiter's are generally found around relatively younger stars. See, these are younger 5 to 6 giga-years compared to the age of the galaxy. These are younger, definitely. So it looks as if Jupiter, like, see, this is, we have not published this result yet. So we are in the process of publishing it. So this is, really the frontier result. It looks as if, Jupiter's, the gas giants started forming only in the last 5 billion years. This is young compared to the age of the galaxy, but but it's a 5 giga-years. It's really long ago. Yeah. So yeah, it is true there is an age dependence, and that is probably what this result is showing.
Yeah, hi Manoj.
Yeah.
Hi. So I have a few questions. So can you tell us what are the advantage of photometric and spectroscopic discoveries of exoplanets? Advantage and disadvantage both.
See there are some selection. See, there are sensitivity issues. So radial velocity technique. So maybe I can show you the equations of that. See it. Oh, sorry. What happened? Sorry. Let me this up again. See, there are some selection effect intrinsic to the detection methods. See, for example, the radial velocity thing. Yeah. Sorry about this. So now if I go full screen, so can you see this? So you see the
I can see.
The radial velocity stuff, the radial velocity semi-amplitude. See, that is the crucial thing, right? You need to detect this amplitude. That is directly proportional to the planet mass, and also the period, inversely proportional to the period, or 1/3. So radial velocity technique will preferentially pick up more massive planets closer to the star, because they are likely to exert more gravitational influence on the star, right? We are measuring the star which is going around. And this was the case in the first 10 years of exoplanet detection. That is why most of the radial velocity detections were what we now call hot Jupiters, Jupiter-like planets, massive planets closer to the star. So radial velocity technique has this sensitivity issue, so it does a selection effect. But now, as and when the radial velocity precision improves, it can detect planets farther and farther away. It's a combination of the orbital distance and the planet mass. Similarly, transit thing, so that will depend on the orbital period or the orbital distance as well. It's easier to pick up planets which are shorter orbital period by transit method. So there are these selection effects, but they are also complementary in the sense that radial velocity technique will give you the mass of the planet uncertain to the inclination angle of your orbital plane, which is that is why the sin I factor comes in. I is the inclination angle. So if your orbital plane is perfectly perpendicular to your line of sight, then you will sin 90. That's 1. So this is MP. But radial velocity will give you the mass of the planet, minimum mass of the planet, and uncertain with the inclination of the orbital period. And transit will give you the radius and the inclination angle. So if you can observe the same planet by both radial velocity and transit, you can measure the true mass and the radius. That's the advantage. But they both have selection effects, inherent selection effects. So one has to be careful about what they so what they unearth or what they discover is not the true sample out there.
Okay, and spectroscopic also the same thing?
Radial velocity technique is spectroscopic technique, whereas transit method is the photometry technique.
Photometric technique.
You just monitor the star, and then when the planet passes in front of the star, there will be a dip in the brightness. Whereas radial velocity, you do spectroscopy and watch the lines go back and forth.
Okay, the one I'm just curious to know. The one question is: does polarization matter here in these kind of observations?
I think it's yeah. So see, the thing is, we are not resolving things. See, we are just observing everything together. So polarization, even if there is some intrinsic polarization, they all could. It depends. In the radio wavelengths, things could be different. See, the planets also can emit in radio wavelengths because of a mechanism called electron cyclotron maze instability. So that is coherent emission mechanism. The emission from the planet. So it happens when the stellar magnetic field interacts with the planetary magnetic field, and then the electrons gyrate around them.
Like Jupiter, when you are saying?
Yes, the auroral emission of Jupiter. Yes. So the auroral emission of Jupiter is an example. So that emission is polarized. The ECMI part. See, Jupiter has several different emission mechanisms. There's synchrotron emission. There's thermal
cyclotron emission.
Yeah. So, but there is at the decameter wavelength at very low frequencies, like 100 megahertz or lower, Jupiter has the decameter emission, and we expect exoplanet if they have magnetic fields, and they're also closer, right? The several of the Jupiter-like planets are very close to the central star, so the magnetic field interaction was much stronger. And in radio, people have been looking at it. We are also doing a survey with GMRT, but there has been no success so far. Nobody has observed or detected.
Nobody has got the signature of the decametric emission from any other exoplanet.
No. That would be a massive discovery.
Just I wanted to ask. My next question was on the same line. Like apart from this optical and IR observations, so does people have observed?
People have. So radio is one such example. People have been looking for it, and without any success so far. There is a tentative claim recently last year, but it's not very clear. So I'll not go into the details of that. But yeah, people have observed exoplanets in X-rays and UV, the transit observation. See, so a particular subclass of planets which are particularly interesting for observations are follow-up observations are transiting exoplanets. So when they transit, you look at them in X-ray, in UV. So the radius of the planet, especially when they have atmosphere. See, the next frontier in exoplanet research is the planetary atmospheres. To study them, you observe transiting planets in X-ray wavelengths, UV wavelengths. So the size of the planet looks different because the atmosphere comes into play. So there are very interesting things going on. I didn't go into the details of that. So that seems to be the direction in which exoplanet research is moving. The planetary atmospheres that can tell us a lot of interesting things. So yeah, to answer your question, yes, in X-rays, in UVs, UV, not. Yeah, in sub-millimeter, millimeter wavelengths, if the planet is young. See, the planet also, most of the, for example, now the older planets, the solar system is 4.5 billion years old. The planets in the solar system mostly reflect starlight in the optical wavelength or infrared wavelength. But young planetary systems, so a Jupiter-like planet which has just formed, that can emit its own radiation from the Kelvin-Helmholtz contraction, the gravitational contraction. If they are sufficiently young, you can pick it up in the infrared or even in the longer wavelengths. If you're
In sub-millimeter, you can say?
Sub-millimeter, not directly perhaps. These are difficult experiments, the direct detection. But you can definitely, if you can block the starlight. So let me give you, I didn't talk about some of the other detection techniques. So if I can quickly show you. This is a star, okay, what you see in the star. So suppose if you block the starlight, say in the mid-infrared or mid-infrared wavelengths, then you can see the planets emitting their intrinsic. See there. So this is the intrinsic emission from the planet in the infrared. So we have about 50 such planets which are directly imaged planets by blocking the central light from the central star. See, that contrast is much better in the infrared. Much lower, in fact. So it's favorable for us for detection. So typically at 4 to 5 microns.
But you need to mask it to see the.
Yeah. Otherwise, the stellar light just overwhelms everything. You need. So these are called coronographic observations. So you block the starlight, and then the planet becomes visible. But in the sub-millimeter, what you see is, I can probably just show you. I had this. You see, the planetary systems are supposed to be formed out of protoplanetary disks. These are gas and dust disks, rotationally supported gas and see. There's a central star. This is a sub-millimeter. We're using interferometer called ALMA. The gaps that you see in this dust disk, these are probably carved out by Jupiter-like planets that are being formed. Yeah. So this is another such planet. People believe this is a planet that is being formed. And see, there are several such disks imaged. There are all kinds of disk substructures, these cavities and openings. So planets are being formed in these disks. So these are picked up by ALMA mostly at 240 gigahertz from the dust continuum emission. You need extremely high resolution for this. So 35 milliarc seconds. That corresponds to 5 AU at the closest. So, yeah.
Yeah, okay. So these are few questions which I had. So if there are some questions from YouTube, so Vedang, is there any question from YouTube? Okay.
So, yeah, thank
Yeah,
you.
we can.
Yeah, we are good.
We can stop here.
So, thank you so much for giving us the talk. This topic was really interesting, and I'm pretty sure our audience have got something from this talk. So, very much thank you to.
Thank you, Jameer, Vedang. Thank you for this opportunity. I hope I was able to convey the excitement of this field.
Of course.
This is a really growing field, and some of you who are interested should read up. And you can write to me if you want. See, in India, there are only a few people who are working on it.
Work in this field.
Yeah, but as I told you, ISRO, our space agency, has plans for sending an exoplanet mission. So we need people, to sort of come into this field, work on it, and expand this further in the country. But
yeah,
this is.
There was one question which I forgot to ask. It was about some study research. So, can you suggest some resources from which one can study about exoplanets?
I mean, yeah. So if you are looking for a kind of textbook kind of resource, then I think the best would be. I think the title of the book is Exoplanet Handbook, or a Handbook of Exoplanet by Michael Perryman. It's a kind of a textbook. It's a treatment is a textbook kind of treatment. So it's pedagogical. So it will be easy to follow. I think that would be the first resource that you should look into.
Yeah. So we will give in this link, like we can put this into our links.
I can send you the reference if you want. I can send a mail, and you can.
That will be great.
Yeah, sure. No problem. Yeah, write to me if you need anything. You have my address. Write to me. I can share the resources and any other information that you might want.
Sure, definitely.
Yeah.
Yeah, thank you, Manoj. So thank you very much.